Related rates with the TiNspire. And just a little bit of background information. I'll try to go quickly through related rates as you've encountered them before. Related rates, that is implicit differentiation with respect to time. We're going to use a TiNspire and we're going to take the given information and find what they're asking for. So a little bit of background information. We have the derivative stated here with Newton's notation. Now the units are a nice giveaway if we want to write it in Leibniz notation. I think I'll do that right now. That's the derivative of theta with respect to time. Theta is in radians and time in seconds. Curiously, they gave us 120 degrees. They gave us theta in degrees. We could quickly convert this to radian. This is very easy for us to do. There's 180 degrees in pi radian. There we go. Divide them both by 60. We got 2 over 3. There we go. 2/3 radian. That's quite easy for us, but back to our notation at hand. And so this one is the derivative of the derivative with respect to time. Leibniz notation would look like this, the derivative of the derivative. When we take the derivative of this derivative with respect to t, let's just take a look at how that'll shape up for us. I'll just write it right over here just as a reminder. I'm going to take the derivative with respect to t of the derivative, like that. And the notation we have then for our, what we just quickly refer to it as our second derivative, would be the second derivative of theta with respect to t. And even our units are helpful in reminding us what the Gottfried Leibniz notation is here. So here we have Newton's notation and Leibniz notation. They give us r is equal to this function right here. So let's first find r. So our solution technique to find r is we just have to take the given information and substitute in the theta given to us. This is where our calculator will hop in and help us for a moment. I'm going to take this function r and I'm going to declare it in my TiNspire. I'll hit the control and then define it as, and let's just type it in, 25 times, and then I'll put in parentheses 1 minus cosine of theta. And I'll include theta, control, come over here and I'll find theta, what's right here, convenient, and one more parenthesis. When I hit enter now, it has defined r. So when I wish to evaluate r at some value, I can make that statement. Here's one way that we can do it. I just copied down this expression that is r, and I will use the control and then we'll evaluate. This little vertical bar means such that, and then I can put in the condition. Theta is equal to, remember where we got theta, theta equals, is it equals sign right here. Now we get to type in 120 if we want to put the degree symbol on it. Remember, if we don't put the degree symbol on it, we'll have to type in the 2/3. There's a degree symbol right here. There we go. Now an enter, and it gives us our answer. Let's go record that. So we have found r is equal to 75 over 2, or 37.5, whatever you would like to write it out as. Now in this particular story problem, I left this part out. I probably shouldn't have, but this r was given to us in feet. So this is in feet. I that was kind of an important piece there. Well, let's go find the derivative, and we'll evaluate that. Now our derivative, r prime, what we want to take a look at is how is r changing with respect to t. Well, that was pretty easy. Now, as we look for r prime, I'm going to bring in some notation. We want r, the derivative of r, so we're going to want the derivative of r with respect to t. We're going to see how that's changing. So this is Leibniz notation versus Newton's notation. And if we look at this, we need to state the derivative of r with respect to t. And you'll notice then, well, wait a second, if I'm finding the derivative of r with respect to t, and I have theta over here, I'm going to need the chain rule. Yep, you'll need the chain rule. So let's bring in the chain rule. I'm going to copy this equation down, just as I did before. I copied it down as I had before, but I distributed the 25. I just thought that might make it a little bit easier. And what I'm looking for is the derivative of r with respect to t. So here's our implicit differentiation with respect to t. We'll differentiate both sides with respect to t. Now as we differentiate this left side, we do have the derivative of r with respect to t. As we differentiate the other side, the derivative of 25 with respect to t is 0. And now I'll find this negative 25 times the derivative of cosine of theta. Now what you'll notice is this is our chain rule right here. So we'll find what our derivative is going to equal. Just a little reminder. The chain rule, when we see it written in Leibniz notation, we really see why we call it the chain rule. The derivative of r with respect to t is the derivative of r with respect to theta times the derivative of theta with respect to t. Now this is where the chain rule gets its name. You can see the notation appears to have these canceling each other out, but keep in mind these are both their own symbol. Hey, we did a little bit of chain work up here, didn't we? Where we let the degrees cancel out. Kind of a fun little connection, and the reason we call it the chain rule. So we do have the derivative of r with respect to this side. Let's go find the derivative of r, which here's r, with respect to theta. So I will have the derivative of cosine. It's a cofunction, so I know it's negative. So negative times negative is going to be a positive 25 sine of theta. That's what this is right here. Let's make a note of that. Don't worry, I'm going to do this with the calculator too. Just going to illustrate how we can do it by hand, and it'll match what we do with the calculator over there. So hang in there, bear with me for just a moment. So here's our derivative of r, just the derivative of r with respect to theta. This is very easy. 25 sine of theta. Now times d theta dt. And that's our derivative of r with respect to time. It looks like this. And we can put that information in so we can evaluate it. Well, let's go see how our calculator will handle this one. Now we've declared what r is equal to, so let's push the menu. And we're going to use our calculus feature and find the derivative. Here we go. The derivative with respect to, I'm going to put the theta in here. There we go. Derivative with respect to theta of r. So I can just type r in here. 25 sine of theta. Now that'll match what we had written down right here. This is the derivative of r with respect to theta. Using our chain rule, we'll just have to add in what d theta dt is, and well, not add in, but multiply. And so we see that d theta dt is equal to 2 as part of the given information. So I'll just make a little note. We're going to multiply this by 2. And so we'll have 50 sine of theta, where theta is equal to, we can input it as 120 if we use the degree symbol, or we can, oh, I forgot the pi on here, better put that in there, 2/3 pi. I saw I was missing the pi in there, 2/3 pi radian. And so there we have it. We could put that in and we could find dr dt. So let's do that. There we got it multiplied by 2. And what we're going to do now is we're going to say such that, which is right here, theta. I'll give you another little secret way to get theta. If you push your pi button, you'll see this theta right here. Just kind of a fun little thing. It's a little quicker. Theta equals, now what I'll do is I'll type in the 2/3 pi, just to remind everybody that if I want to enter it as 2/3 pi radian, I don't have to put anything else. So if I want to enter it as 120, I have to use the degree symbol. So we'll just do that. 25 square roots of 3. I'm just including this radian measure because I had forgot to write the pi up there. Now I'm trying to redeem myself. And so we have found 25 square roots of 3. Now if r is given to us in feet and time in seconds, this would be feet per second. Maybe I should get an approximation of that. Now that is feet per second. Like so. Alright, now all we have left to do is find the second derivative. So let's give that a go. So let's find the second derivative of r with respect to t. I think I'm going to need another piece of paper. I do want to point out, though, that I have the derivative of r with respect to t conveniently stated right here. I have it conveniently stated right here. So I'm going to go and take this statement, copy it over, and then we'll take the derivative with respect to t of that derivative. So I've carefully copied down the derivative of r with respect to t, and I'm going to take the derivative with respect to t so I can find the second derivative. Alright, so I'm going to differentiate with respect to t. Now on the left side, what we'll find is we have the second derivative with respect to t, conveniently written in Leibniz notation. On the other side, we will need our product rule. Do you remember your product rule? We're also going to need the chain rule. We see that the characters here don't match, so we're going to need both the product rule and the chain rule. To simplify things a little bit, I'm going to move this constant 25 out in front of the derivative statement. So hang tight as I do that. This simplifies it just a little bit. So we have our second derivative of r with respect to t. We're using our product rule now. Let's put a big old square bracket here to hang tight. As we've got the first, because I'm taking the derivative of this product, I have the first times derivative of the second plus the second times the derivative of the first. And that's the product rule that we're differentiating right here. So let's give it a try. First times the derivative of the second plus the second times the derivative of the first, but that's the derivative with respect to t, so here comes our chain rule. Alright, I think we've got it. Don't worry, I'm going to do that with the calculator also. Let's simplify this a little bit. And simplified it a bit. Second derivative with respect to t. I have the derivative times itself twice, so I just wrote that as quantity squared. Now, when we're evaluating this second derivative with respect to t, we were given theta, and we were also given the second derivative, and we're given the first derivative, and again theta. So remember, we have all of the information. As long as we speak the language, we'll be able to get this information input in there. Let's try it right now. Let's take the information that we have, substitute it in here, and then see what we get for that second derivative. Then we're going to go take a look how we can do it with the calculator as well. Now as I entered in theta, I used 120 with degrees. The second derivative was equal to 0.2, so I just indicated that with an arrow through here. The first derivative was equal to 2, and that is squared, so I won't forget to square it. So I entered this into the calculator, and I'll show you what I got. You can check to see if you got the same thing. As I entered this in, I got a negative 45.66987, and I'll let you round to where you see fit, but that would be in feet per second, feet per second squared, like so.